Good afternoon, everyone, and good morning to others. Thank you so much for joining us. Our webinar today is entitled The New GI Effects Report, Advancing GI Testing Through Data Analysis. And our prestigious speaker is Dr. Michael Chapman. My name is Dr. Lenore Powell, and I am a medical education specialist in Genova's Atlanta branch. I am going to serve as the moderator for today's webinar. We'd like to welcome Dr. Michael Chapman. Dr. Chapman is a licensed naturopathic physician who graduated from Bastyr University in Seattle, Washington. Upon graduation, he spent 3 years in private practice before joining the team at Genova Diagnostics. His areas of clinical focus are hormone regulation, gastrointestinal health, and autonomic balance. Prior to med school, Dr. Chapman earned his Bachelor of Science degree from Indiana University with a focus in neuropsychology. He later worked as a microbiologist performing pharmaceutical research on cancer cell lines. In addition, you will have access to the presentation and the slide deck on our website within a few days after the webinar. You can access these resources, previous webinar recordings, brief video modules, and other materials by clicking the Clinicians tab on the homepage. With current events prompting many clinicians to do non-acute patient appointments through telemedicine, I want to remind you that we have many non-invasive urine, saliva, blood spot, even stool testing collection packages that can be shipped directly to your patients for specimen collection at home, and the requisition can actually be completed online. For more information, please visit your LiveGDX account. I'm now going to turn over the role of presenter to Dr. Michael Chapman.
Excellent. Thanks, Lenore, for that introduction. Let me just grab the screen here. Hello, everyone. I hope you're all hunkering down and doing well. But before we get into today's topic, I'd just like to acknowledge the fact that I'm sure a lot of you have had to adjust, rearrange, or completely change your working situation in response to the COVID-19 pandemic. We keep using phrases like unprecedented and unpredictable times, which is certainly true. And we at Genova would also like you to know that we are here to support you in your practices. We have the capacity, like Lenore mentioned, for online ordering, and we'll drop ship test collection packs directly to your patient stores. So keep this in mind as many of you are transitioning or have transitioned to working from remote locations and working from home. With that being said, today I am here to talk to you about our very exciting upgrade to the GI Effects Report. The origin story of this upgrade is, in essence, it's based in a couple different aspects. First, we're always asking the question of how to make a more clinically useful report. Sometimes that means simplifying certain aspects that are challenging. Other times we enhance the clinical utility of the report by adding elements. In the case of this upgrade, we're actually doing both of those things. Second, we listen to you, our customers, and your great feedback on what needs more information. So, for example, with this report upgrade, we spent a tremendous amount of time and energy performing data analysis on the 24 commensal bacteria. So we can begin to try to unravel that knot of how these bacteria play a role in GI function, and specifically dysbiosis, which we're going to go over quite a bit today. And then last, we want to make sure that you have a report that's actionable, right? We want you to have a report that you can pick up and from the first page get a good understanding of how these results relate to your particular case and point you towards some ideas of what your next steps might be. So with that, let's dig into this new GI effects. Some objectives for today's presentation: we're going to explore the new features of the GI Effects Comprehensive 2200. We're going to become familiar with how to use this new DIG scoring system, which we'll talk about. We're going to understand the clinical utility of some novel microbiome biomarkers, which is very exciting, and then review the components of the GI effects test. If you're new to the GI effects, we'll do a quick little review of some of the elements that you may not be familiar with. So here is a brief look at the pages of the report. And one thing I want you to know right off the bat is that there's no changes to the biomarker section of the report. The only changes that we're making are we're taking the front page of the report, which was an interpretation at a glance overview page, and reworking it so it essentially has a lot more clinical utility for you, the physician. So don't worry if you're thinking that some of your favorite biomarkers like pancreatic elastase or calprotectin are going away. The truth is nothing is going away from the report. We're just adding some layers of clinical utility. So with that as our premise, let's take a look at the brand new front page of the GI effects report. Here is page 1, and this page is broken down into 3 main sections. At the top, we have a results overview graphic, which is an evaluation of the key functions of the GI tract. Then we have functional imbalance scores, which is a numeric scoring system based on the results of the biomarkers that are listed underneath. And then therapeutic support options, which is brand new and is for an ease of use interpretation and implementation of your treatments. Let me talk a little bit about the results overview graphic. When you take a 30,000-foot view of GI health and ask the question, what are the core features or functions of GI health and the GI tract, you really come away with these main categories of digestion, inflammation, or immune response, as some people will tether it to, and the gut microbiome. And this is not just unique to us. You find this particular DIG format in other educational institutions. And the results overview graphic is designed to give you a quick report of findings based in these 3 key areas, right? That's why we have around this circle digestion, inflammation, and gut microbiome. But then when you go a step further and you ask the follow-up question regarding what are the key functions related to the microbiome, these include 3 additional elements: infection, metabolite imbalance, and dysbiosis. And we separate infection and dysbiosis intentionally, right? They're 2 separate things. An infection is the ability or the aspect of having a potential pathogen or true pathogen as part of the microbiome that shouldn't be there, which is different from dysbiosis, which could just be simply an imbalance of commensal bacteria unrelated to pathogens or potential pathogens. So you can see that now we have these 5 key areas of interrogation and investigation. Here again is the top of the report with the results overview graphic and a key for the colorimetric icons. So essentially the way that this works is that green indicates a low need for support, gray indicates optional need for support, yellow moderate need for support, and red indicates a high need for support. So for this particular individual, they have a moderate need for digestive support because you can see that yellow for maldigestion. They have a high need under the category of gut microbiome, specifically because of dysbiosis and infection. And also you can see that their inflammation category is also indicating a high need for support. Then underneath the results overview graphic, we expand out the analysis of the key functional areas. And here the color icons are converted into a functional imbalance score. So the functional imbalance scores are a numerical way that you can rank, stack a patient's results and prioritize areas of support, right? You're going to think about treating the higher scores a little bit more with more importance than the scores that are not so high. So for instance, here, I might be thinking about treating inflammation, dysbiosis, and infection before supporting digestion and maybe prebiotic support, although you might want to think about instigating all of those therapies for this individual. So the question then becomes, how did we arrive at the scores? Well, the scores are based on a 2-factor weighted algorithm, which takes into account the severity of abnormal biomarkers for each section, which are listed just below the score, and it takes into account that particular biomarker's clinical importance relative to the others. So for instance, if we just look at this first score here under maldigestion, which is a 5, you can see the biomarkers that played a role were pancreatic elastase, products of protein breakdown, and fecal fats. Now the green circles show you that products of protein breakdown and fecal fats were within the reference range as compared to pancreatic elastase, which here is on the borderline low side as indicated by a downward facing triangle. And this is the biomarker that played a role in generating that 5 for a functional score under maldigestion. And for general reference, the higher the score, the greater the need for support, and the higher the score, the greater the dysfunction. At the top, we have a key for the scoring system, so you can have a direct understanding of what a 2 means versus a 2 or a 3 or a 4, 6, and then underneath that, we've actually mapped these functional areas to what it means from a clinical treatment standpoint. So for maldigestion, this is going to infer a need for digestive support, inflammation is going to infer a need for inflammation modulation, and so on. And then finally, underneath the biomarkers that contribute to the scores, which are static on every report, we have therapeutic support options, which we'll go into next. The therapeutic support options are here to help you personalize your therapies. These are going to be static on every test, and what that means is that these therapeutic support options do not change based on the score. They will always remain the same depiction here. These are provided as an educational resource because ultimately treatment decisions are left up to you, the clinician. But one of the ways I like to think about using this is, if you have your patient in front of you, one option is you could go through, you could tell them and highlight the scores that you're really wanting to focus on, and then you could even highlight or circle the particular therapies that you might be instigating. So then the patient has a direct one-to-one understanding of why they're getting what they're getting from a treatment perspective and how that relates to their individual results. So that's page 1. That takes us to the next 2 pages, which are strictly dedicated to a microbiome analysis. So previously we had 1 page for a report synthesis. Now we're expanding that into 3 pages, including 2 full pages dedicated to the microbiome. Why are we dedicating 2 whole pages to the microbiome? Well, clinicians often struggle with what to do with this DNA PCR analysis of the commensal bacteria. And there's some good reasons for the struggle. There's a lot of historical limitations. For instance, methodologies in the literature differ. What does that mean? That means that in some studies, the methodology that's being used in the published literature is a PCR method, whether that's 16S. In other studies, that might be real-time PCR, and they might have different findings. Not only that, sometimes when the same methodologies are being used, we're still finding discrepant results in publications. Another historical limitation is that some of these bacteria have virtually unknown clinical importance. And then finally, there's very little research into bacterial patterns, which is one thing that here at Genova we were specifically interested in. So what did we do? We tried to use AI and machine learning to develop a cluster analysis to profile thousands of GI effects commensal bacteria results. And this helped us to pave the way toward understanding shifts in microbiome patterns that are associated with clinical symptoms. And we'll go into what that means and how we generated some of these novel biomarkers in a second. But one of the things that's really, really helpful is that now you're not having to compare your lab results to the published literature. You're comparing apples to apples instead of apples to oranges when you're sending it directly to us, because our research is using the same methodology that you're getting from the stool testing. Same methodology, same DNA probes, and same commensal bacteria, which is different if you're trying to compare your patient's results to maybe the published literature, which has different methodologies, different DNA probes, and such. So this is what pages 2 and 3 look like now. Again, this is just dedicated to a microbiome analysis. And when we're thinking about the microbiome and how to interpret it clinically, we are essentially saying, what are the 3 main categories that are important to focus on? And what we uncovered here was that abundance, patterns, and then balance really are kind of the 3 categories that we should be focusing on. So starting with abundance, we have this biomarker called the total commensal abundance. Now, it's not completely novel or completely new. This was previously described as the relative abundance, but we tried to make this a little bit clearer to demonstrate the quantity of commensal bacteria compared to a healthy cohort. So this is taking those 24 commensal bacteria and essentially saying how many bugs are there compared to this healthy cohort. And the U indicates that the patient has overall more or less bacteria. That's going to be what slides right and left. So the way that this works is that a shift to the right indicates that the patient has more overall commensal bacteria compared to the healthy cohort. And this may be indicative of a potential microbiome overgrowth, such as in small intestinal bacterial overgrowth or SIBO, or maybe just in general microbiome overgrowth that could be considered even in the large intestine. We may also find a shift to the right due to recent supplementation with probiotics. That's a possibility as well. A shift to the left indicates that a patient has overall less commensal bacteria and may be indicative of potential microbiome deficiency, such as following antibiotic use. May also indicate that there's a diet low in fiber or prebiotic foods, and that's what's contributing to the microbiome potential deficiency here. So this is the total commensal abundance. Now, after abundance, the next section we have is patterns, or dysbiosis patterns. Now, this is going to require a little bit of explaining because these are brand new biomarkers that are super exciting. These are unique to GI effects Genova's testing only, and this is what's based on internal data analysis of these 24 commensal bacteria. What we were able to do is, when we did data analysis, we were able to determine that there's different types of patterns going on and that are associated with different clinical presentations. And the two big ones that we're reporting now are the inflammation-associated dysbiosis score, which is an indicator of a dysbiotic pattern associated with GI inflammation, again, strictly based on the 24 commensal bacteria and one stool biomarker. And then the second marker here is a methane dysbiosis score, which is an indicator of a dysbiotic pattern associated with methane production. And we'll talk about these individually here next. So the inflammation-associated dysbiosis score, as I mentioned, this is a specific dysbiotic pattern that's associated with inflammation. How did we determine that? Well, we took the bacteria on page 4, these 24 commensal bacteria, and we looked at them and said which ones correlate with the inflammatory biomarkers, which ones positively correlate, and which ones negatively correlate. And from that, we were able to determine and derive an algorithm that can predict, or at least determine, the likelihood of inflammatory biomarkers. And after we did that, we actually published an article. And in this article, there's two separate studies. The first study, we used our own internal database of over 7,000 tests. And then the second study, we partnered with UCLA Medical Center. And what we were able to do was demonstrate that this novel IAD score, remember, that's based on the 24 commensal bacteria and a stool biomarker, that correlated to all of our inflammatory biomarkers. So you can see here with this chart, fecal calprotectin went up as the IAD score went up, eosinophil protein X went up as the IAD score went up, and fecal secretory IgA went up as the IAD score went up. So we demonstrated that this score does correlate to the inflammatory biomarkers, and this score was able to distinguish disease cohorts between inflammatory bowel disease and IBS and celiac. And actually, this top score was based on the Genova study, distinguishing IBS from IBD. And then the bottom one here is the IAD score, distinguishing Crohn's and ulcerative colitis from the UCLA study. So what does this mean clinically? Some key takeaways is that the IAD score is able to distinguish a commensal profile that's associated with inflammation in the GI tract, and was able to distinguish ulcerative colitis and Crohn's disease from a statistically significant study. What does it mean if the patient doesn't have a history or a diagnosis of inflammatory bowel disease? Well, I would certainly be looking at the inflammatory biomarkers and asking whether there's the likelihood of some inflammation going on, because this is essentially predicting a dysbiosis that is associated with inflammation. But what if there's an elevation in the IAD score and there's no presence of inflammatory biomarkers? What does that mean? Well, because this is a novel biomarker, we don't quite know the answer to that just yet. But because it's an indicator of dysbiosis that is prone towards inflammation, my question would be, is this potentially an early indicator of an inflammatory pattern or an inflammatory process? Again, we don't know that for sure yet, but that would be where I would be heading from a clinical suspicion standpoint. So we talked about that first pattern, the inflammation-associated dysbiosis pattern. The second pattern is called methane dysbiosis. And this is one that's, like it sounds, it's associated with methane production. We were able to develop this using an algorithm-derived score that predicts higher methane production based on SIBO tests. And again, with this particular score, it was based on the commensal bacterial profile and some stool biomarkers that generate this methane dysbiosis score. So how did we get there? What we did was we pulled GI effects results from patients who had also, within a similar time frame, done and completed SIBO breath tests. And then we asked the question, what do their commensal bacterial profiles look like when they had an elevation of methane on their SIBO test? This is how we were able to derive that information around methane production. And why is this even important would be one of the questions I might be asking, is that methane is produced in the GI tract through the consumption of hydrogen, which is produced by other bacteria, and the predominant methanogen in the GI tract is Methanobrevibacter smithii. It's actually not even a bacteria, it's what's called an archaea. And we know that intestinal methane production is associated with a slow transit time, constipation, and actually some clinical conditions like obesity and diabetes. But another thing that's important to understand is well captured in this 2020 American College of Gastroenterology paper, which suggests a new condition named intestinal methanogen overgrowth, or IMO, to represent an elevation of methane production on a breath test. And they summarize here, the problem then becomes one of nomenclature. Excessive methane production cannot be caused by bacteria, but is rather due to archaeal overgrowth. So IMO may be more appropriate than SIBO, or what a lot of us have called methane SIBO up until this point. And furthermore, methanogens do occur in the small bowel in individuals with positive methane breath tests also exhibit increased methanogen levels in stool, which means they may be both in the small and large intestine. So therefore, it's not altogether correct to use the term small intestinal overgrowth, but should be using IMO to be more accurate. And now we've got a biomarker that is able to associate higher levels of methane production. Here's the other interesting bit about methane, is that with increased production of methane, we found that there was lower levels of inflammatory biomarkers. And you can see that here. Lower level of fecal calprotectin, lower level of EPX, lower level of fecal secretory IgA. And what's more, we found increased eosinophil protein X levels below detectable values, and an increased number of fecal secretory IgA below detectable values. So it appears that there's a statistically significant lowering of the immune response that's associated with methane production. So there seems to be this intertwine between methane and immune function. And one other interesting bit was that individuals with higher methane production had a statistically significant higher rate of infection with potentially pathogenic organisms, specifically Blastocystis and Entamoeba histolytica. So the hypothesis going is that with decreased immune reactivity and increased rates of potential pathogens, methane production may actually contribute to intestinal barrier dysfunction at high levels of production. So methane production may be suppressing immune response in the GI tract. And we even have a proposed mechanism. Methane production has been associated with decreased postprandial serotonin production. And that makes sense because serotonin is responsible for peristaltic activity. That might be the link between methane production and constipation. But furthermore, serotonin in the GI tract is the main mediator of intestinal immunity, including eosinophil and neutrophil recruitment, B cell regulation, and attractant for dendritic cells. So the clinical significance here is that a high methane production may be slowing transit time and may be suppressing immune function and barrier function in the GI tract. So we've talked about the IAD score and the methane dysbiosis score. Now, what happens if we put them together? If we look at the inflammation associated dysbiosis score on a spectrum here, and then we compare that to the methane dysbiosis score, which we're hypothesizing has to do with immune suppression, and you plot those on a 2x2 grid, what you get are these 4 distinct zones which have different clinical uses and different clinical therapies that you might think about. And we'll talk about that here in a second. These dysbiosis zones, like I said, are developed plotting this inflammation-associated dysbiosis score against the methane score and have unique characteristics and clinical considerations. For example, zone 1 at the bottom left represents a low likelihood that the commensal pattern is associated with either inflammation or intestinal methanogen overgrowth. So this is least likely to require microbiome modulation. So this is kind of the sweet spot where we would like to see a lot of our patients. Zone 2 is a pattern of bacteria associated with potentially suppressed immune system and barrier dysfunction, and intestinal methanogen overgrowth is strongly associated, making treatment of methanogens, or at least follow up with something like a SIBO breath test to determine methane levels, that makes a lot of sense. Zone 3 is actually not very common, because it turns out that people with a higher methane score tend to have lower levels of inflammation, as we already talked about, and vice versa. People with a higher IAD score have lower levels of methane. So actually zone 3 is not very common, but if you were to find a patient in this particular zone, you still have a robust commensal abundance, and the use of antimicrobial agents, if you were going to treat their methane production, is relatively safer. And that's different from zone 4. In zone 4, you're going to have a high degree of suspicion of inflammation, and the patient's much more likely to present with loose stool, diarrhea, and all those things that you're concerned about when it comes to inflammatory bowel disease. And furthermore, from a treatment standpoint, in zone 4, you're going to want to be most careful when considering the use of antimicrobial agents, as this could worsen dysbiosis because they already have a lower total commensal abundance. So we've talked about a total abundance. We've talked about these dysbiosis patterns. Now the last element is commensal balance. And the new GIFX looks at balance in 2 different ways. The first one is this commensal balance graphic, which you may have seen before if you're familiar to the GIFX, but this is based on clinical populations such as IBS, mood disorder, chronic fatigue, autoimmune, different clinical populations versus a healthy cohort. The second aspect of balance is relative commensal abundance, and this is comparing phylum abundance against a healthy cohort, and we'll talk about these 2 individual biomarkers next. The commensal balance graphic is a composite of 2 measures. So this up-down y-axis is called the healthy pattern continuum, and this algorithm helps us differentiate healthy and unhealthy commensal balance patterns. The x-axis is called the reference variance score, and what this is actually just looking at the 24 commensal bacteria and asking the question, how many of them are outside reference range? So that's why it's a scale from 0 to 24. There's 24 different commensal bacteria. How many of those are outside reference range? And this helps us to predict the balance of the commensal bacteria. How? That might be one of the questions you're asking. Well, if we look at these 2 individual axes individually, on the left-hand side, this healthy pattern continuum, you can see we've got the data plotted here of the healthy cohort as compared to the IBS group, and that orange bar represents the mean. So you can tell very distinctly that the healthy pattern continuum has a much higher value in the healthy group as compared to the IBS group. Conversely, the reference variance score to the right of that, if you compare these 2 means, both of which are statistically significant, the healthy cohort had lower reference variance score compared to the IBS group. So when you plot both of these against each other and look at something like IBS, you can see that the healthy group clusters towards the top left as compared to the IBS group. But that's not even the interesting bit. The interesting bit is that when you look at chronic fatigue, you find a very similar pattern. When you look at autoimmune, you find a very similar pattern. And so that's how we were able to generate this commensal balance graphic. And you can compare your patient's balance against these different disease groups. And more likely than not, if that U is showing up in that green balanced area, they have a microbiome that resembles much more of the healthy cohort as compared to the unhealthy disease groups. The next aspect of balance is what's called relative commensal abundance. And this is not completely new. What we tried to do was take the relative abundance and create a clearer way to visualize the differences between the major groups of bacteria. Previously, we had these two pillars, and it's a color-coded stacked kind of bar graphic. And what we're trying to say there is, what are the differences between the patient results and the healthy cohort, which is circled here? It's a little challenging because if you're trying to ask the question, well, how much of that light blue bar is there compared to the healthy cohort, or is that portion that's purple a little bit bigger or smaller? It's a little tricky to see. So we created a new way to depict this, and it looks like this relative commensal abundance graphic. And here you can see with each phylum, does the patient have overall more or less of that phylum compared to the healthy cohort? Now, clinically, when we're talking about analyzing bacterial phyla, there's some key points to keep in mind. Bacterial phyla are very broad categories that encompass a large number of different microbes. So within each phyla, there's likely organisms that are positively associated with the clinical condition, and then some organisms within that same phyla that are negatively associated with the clinical condition. So it can become really tricky when you're taking the lens and zooming out to the perspective of phyla. And a good example is proteobacteria phyla. There are some proteobacteria that are associated with LPS production and some that are inversely associated with LPS production. So what does it mean when you're just talking about proteobacteria as a whole? It's kind of tricky to understand. The other thing is that literature is mixed regarding clinical claims based on bacterial phyla. So for example, the Firmicutes bacteroidetes is a classic ratio that we've looked at, but it has all sorts of mixed clinical claims with respect to metabolic syndrome. And that goes for a lot of these bacterial phyla comparisons because, like we said in point one, they're just very broad categories that oftentimes encompass members in different types of bacteria and bacterial species and genus that have completely opposing clinical associations. Last, always look at the individual bacteria that are contributing to the phyla for more specific clinical associations and interventions. That's going to help you modulate the microbiome a lot more efficiently. But all that being said, you can derive a little bit of information from looking at these as it relates to balance, and that's why it's in this balance section, because we're trying to determine, is there a good balance? Does the patient result resemble the healthy cohort, or in this case, does it look really, really different? Whereas here you can see there's a lot of these individual bacteria phyla that are greater than the healthy cohort, much greater than the healthy cohort. And then we've got a little bit of clinical commentary here to help you understand what are some major players when it comes to a treatment perspective or a clinical association perspective that can swing these the patient results. And that's just a starting place. I think a nice follow-up is that when we think about gut microbiome modulation, we know that the microbiome can be modulated by so many different factors. That can be diet, prebiotic, postbiotic, probiotic, that can be physical activity or sleep that can modulate the microbiome. And often, one of these interventions doesn't just move one bacteria, right? These bacteria are all integrally related. So if you make a dietary change, it's not going to just change one bacteria, it's going to change multiple bacteria. So one of the things that we suggest is using Genova support materials for more information on how to modulate the microbiome and to shift these bacterial communities and impact the relative commensal abundance. So we're coming out with this commensal bacteria chart, which actually goes through all 4 of the commensal bacteria, all 24 of the commensal bacteria, talks about what are some things that increase those levels, decrease those levels of that bacteria, and what are some clinical conditions that are associated. So use these support materials when you're thinking about modulating the relative commensal abundance. So from a recap of the microbiome synthesis, pages 2 and 3, here's what we've got. We've got abundance with the total commensal abundance, excuse me. We've got pattern with the dysbiosis patterns and these novel biomarkers, the inflammation-associated dysbiosis score and the methane dysbiosis score. And then we've got balance with the commensal balance, which you're familiar with, and the relative commensal abundance, which you might be familiar with. So as a whole, with a recap to the changes, here's what we have. We have page 1, which includes a results overview graphic, functional scores, and then therapeutic support options on page 1. Page 2 includes the elements of microbiome abundance and microbiome patterns. And then page 3 talks about microbiome balance. Well, you might be asking, what else? Well, there's the rest of the report that we have, and none of these biomarkers have changed, like I've said. So pages 4 onward include all the same elements that you're familiar with. And if you want more information, education on how to interpret these, I would suggest going to our website. We've got our module called GI University, where you can learn more about this, all the rest of the tests. But we'll briefly go through some of the key points here, because it does relate to some of the changes. So for instance, with our biomarker page, the biomarkers are separated into digestion and absorption, which play a role here in the maldigestion icon. Inflammation and immunology biomarkers, which trigger the inflammatory score, and gastrointestinal microbiome metabolite biomarkers, which play a role in the metabolite score. So here's the maldigestion score and the biomarkers that feed it: pancreatic elastase, products of protein breakdown, fecal fat. And just very briefly, pancreatic elastase is a marker for exocrine pancreatic function, and products of protein breakdown and fecal fat tell me about how well we're digesting protein and fat. And that is why they're playing a role in the score for maldigestion. The next one, inflammation, immunology, we have these markers. Calprotectin, which is a marker for neutrophilic inflammation in the GI tract, helps us distinguish things like inflammatory bowel disease from IBS. Ulcerative colitis and Crohn's helps us distinguish that from an IBS. Eosinophil protein X, which is an IgE-mediated inflammation marker. So this helps to tell us about whether there's any sort of food allergy on board or IgE-based inflammation. And then finally, fecal secretory IgA, which is, I think, a little bit of a canary in the coal mine marker that helps tell us about barrier function, potential dysbiosis. Anything that's disturbing the mucosa is going to result in elevation in fecal secretory IgA. All 3 of those play a role in that inflammation score. Then the biomarkers that play a role in the metabolite imbalance or metabolic imbalance score are these short chain fatty acids like N-butyrate, acetate, and propionate, which are made when bacteria ferment fiber in the GI tract. Most of the short chain fatty acids we think of as being beneficial, so that's why we want to see elevated, nice, high, robust levels of short chain fatty acids. And if they're not elevated, we'd be thinking about intervention with either prebiotics or fiber. The last one here, beta-glucuronidase, is actually an enzyme that's related to recirculation of fat-soluble hormones and toxins. These are all gut bacterial products, and that's why they play a role in this metabolic imbalance score. The next page is the Commensal Bacteria page. We talked quite a bit about how this is used to create the microbiome synthesis pages. But you know, these individual bacteria have unique clinical associations and importance to GI health all by themselves. And I would like to make a little bit of a plug for a webinar that we previously did in November. Dr. Christine Stube did a webinar titled Understanding the Clinical Significance of the Commensal Bacteria, where she actually went through a lot of these individual bacteria individually and talked about what they mean from a clinical utility perspective. So I just like to plug that if you want to really dig into these 24 commensal bacteria. But just as a little bit of a highlight, some of the ones that I really thought were interesting, the Bacteroides species is correlated to diets rich in animal protein and fat. And these Bacteroides produce a lot of different metabolites, including beta-glucuronidase, secondary bile acids, propionate, products of protein breakdown. And overall, we're associated with reduced microbial diversity and insulin resistance. So that's kind of an interesting one to keep an eye on. It's increased in diets that are high in red wine, animal-based foods, and high-fat diets, decreased by things like inulin and green tea. Clostridium is always one that gets a lot of attention because we think about C. diff, but Clostridium does have over 100 species in that genus. And they do a lot of different functions. Some of them produce really great products. Some of them produce things like beta-glucuronidase, hydrogen, secondary bile acids. So it's a really broad category. And even some of them are necessary for immune homeostasis. So don't paint all Clostridia with the same brush. Another interesting bug on this page is the sulfur Vibrio piger, which has been shown to there's an increased risk for IBD, colorectal cancer, and visceral nerve sensitivity in some studies, and is increased in animal studies with a high fat, high sugar diet. And another one that we talked about briefly, which is not actually a bacteria but an archaea, is the Methanobrevibacter smithii, which is a methane producer, plays a strong role in that methane dysbiosis score that we were talking about, and is associated with constipation, obesity, prediabetes, obviously decreased by antimicrobial therapies like rifaximin and yamycin, but also things like statins, garlic oil, and some probiotic strains. And last but not least, there's a little bit of a darling out there, Akkermansia mucinophilia, which lower levels are associated with all types of clinical conditions like obesity, diabetes, inflammation, insulin resistance, gut permeability. Seems to be very important in improving intestinal barrier integrity, and actually being developed as a probiotic supplement for metabolic conditions. So interesting one that we have on the report as well. This is decreased with low FODMAP diets, which is not too surprising because low FODMAP diets are essentially starving a lot of the commensal bacteria. After that particular page, if you're moving on to the report, we have a culture analysis where you're going to pick up things like Klebsiella, a potentially pathogenic bacteria, or truly pathogenic bacteria like Salmonella. The culture analysis also includes the mycology, which you'll find things like Candida and other yeast species. And then we also have an add-on, which is a KOH prep for yeast. Anything that we find under the culture analysis, we're going to do sensitivity testing on. So whether that's azole antifungals or natural agents for yeast, or bacterial sensitivities using prescriptive agents or natural agents, that's going to come automatic if we find a potential pathogen. Just really briefly wanted to address something that we hear a lot and we get a lot of questions here at Genova and on the medical affairs team, is that this thought that culture is not a good method to pick up yeast. Well, this, in our opinion, is flatly untrue. I say that with a fair amount of confidence. Yeast, and here's why: the yeasts are very simple and straightforward organisms to culture. They tolerate a wide range of temperatures and conditions. So usually we're not concerned about yeast dying in transit or being suppressed in transit in response to temperatures. We're actually more concerned about making sure that we're stabilizing yeast so they don't competitively overgrow. And we do that with a lot of fixatives and stabilizing methods. Yeasts are not as finicky as bacteria on whole. So if a patient has a yeast overgrowth, or particularly Candida albicans, which is the main one that we're really focusing in on from a clinical perspective, we're absolutely going to be able to culture Candida albicans and these yeasts that we're clinically concerned about. But the question is, what about PCR for yeast? Because we have looked into PCR testing for yeast, and one of the things that's problematic about PCR testing for yeast is that our own internal analysis shows that the majority of samples are gonna have yeast in it. Yeast are part of the microbiome, meaning they're part of the microbiome. And what's more, a lot of yeast are coming from the diet, they're transient or dead. And so what does it mean when you find a positive for yeast on a PCR test? Because you're gonna find it. You're gonna find it almost all the time. And the other thing that's problematic about PCR testing for yeast is that there's many times when we've cultured a yeast out and assays have failed to pick it up from a PCR testing. And so what does that mean? Well, how is it possible that we're detecting a live, cultivable, recoverable organism and then it's showing up negative in PCR testing? Well, we'll talk about why that might be in just a second as it relates to parasites. And with that, what about parasites and how are we detecting parasites? Well, methodologies for parasite detection include microscopic ONP, enzyme immunoassay, and PCR testing. All of them have their positives and negatives. So microscopic ONP, the nice thing is that you're able to see all and any and all parasites that are present in this stool specimen. So it's a really great net to cast because you're going to see anything that could potentially be there. Not the case for enzyme immunoassay or PCR testing. With those, you have to have a particular either toxin, or you have to have a particular EIA kit or a PCR probe for each individual organism. EIA is useful for detecting particular toxins and does have a bit of a higher sensitivity for microscopic than microscopic ONP. And then PCR does have a high degree of sensitivity, but it doesn't really tell you about the viability of the organism. So that's one limitation, and you have to have a probe for each organism. So what we feel are best practices around parasite testing is to use multiple methodologies. Use PCR technology for the most common pathogenic parasites, and then use microscopic ONP to rule out other infections. And this is what that looks like. You can see the microscopic ONP page here, and then after that, the parasitology via PCR for the most common organisms like blastocystis, dientamoeba, giardia, etc. By using multiple methodologies, we had the first stool test to combine both ONP and PCR, and it actually gave us some really interesting data that I'd like to talk about just real quickly. I know we're running up on time here, but if we wanted to compare, and we did, microscopic ONP versus PCR, we wanted to answer this question of which is better, right? We always hear that, you know, the PCR testing is more sensitive, it's more specific, it's going to help you determine way better than a microscopic ONP. Is that true? Because now we had both on board. And when we looked at blastocystis as an example, we found that, if you look at that pie chart under A, we found that both were, in positive cases, both microscopic ONP and PCR were both positive 58.9% of the time. However, when there was a discrepancy, this is where it gets interesting. ONP missed the presence of blasto in 14.3% of positive samples, but PCR missed the presence of blasto in 26.8% of positive patients, meaning that if there was a discrepancy, it was more likely that the PCR was incorrect than the ONP. And so the big picture for that is there's methodologies have both benefits and limitations. And one of the things that we have learned is that a limitation with PCR is that that reaction can be inhibited by other things in the stool. And most likely that's bile acids or short chain fatty acids that actually kind of mask the ability to detect certain things via PCR, especially things like blastocystis that we found, and potentially other parasites and yeast for that matter. And this has actually been well established, this PCR inhibition effect. So that's what takes us back to multiple methodologies for parasite detection is really the best way to go. And lastly, not least, we have additional results on the GIFX report. We have fecal occult blood, color inconsistency as reported by the patient, and then a macroscopic exam, or what's called a direct exam for parasites, is also available as an option. We do have additional add-on testing, zonulin family peptide, and then add-on testing for H. pylori, Campylobacter, C. diff, Shiga toxin E. coli, and fecal lactoferrin, all available as add-on tests. And that is essentially the changes and the non-changes that have occurred with the GI effects report. As we said, the biomarkers are the same, and what we've done is added layers of clinical utility. These first 3 pages, hopefully we're super excited to announce, and hopefully you're excited to begin using in your clinical practices, both the functional scores, the therapeutic support options, the full microbiome synthesis. All of those elements are going to be part of the new report going forward. And that is all I have for today's webinar, Dr. Powell. I would be happy to open the floor up for questions.
Absolutely. I hope everybody enjoyed that presentation as much as I enjoyed the presentation. We do have quite a few clinical questions that were asked throughout the presentation. But before I address those questions, remember that all previous webinars that Dr. Chapman referenced in his presentation, they are available on our website under Webinar Archives. And we do have the GIFX Combo Support Guide available for you to download under the Handouts tab at this moment. In addition, a few people asked for access to the article that was cited during the presentation, and that article is available as a full PDF download on your common sites where you can get articles, whether that's Google Scholar or PubMed. So let's begin with this first question. We had quite a few that dealt with the IAD score. So what are potential next steps for following up when we have an elevation with the IAD score?
Yeah, that's a good question. So when I think about the IAD score, what I'm really thinking about is we've got a microbiome pattern that's associated with inflammation. So what I would like to do is first check the actual markers for inflammation, because remember, the biomarkers, the inflammatory biomarkers don't play a role in that IAD score. It's just the commensal bacteria for the most part. And so the next step is to go and check the inflammatory biomarkers. Are those elevated? Which ones? And I would be specifically looking at maybe calprotectin, because calprotectin is a marker that helps us distinguish inflammatory bowel diseases from irritable functional bowel diseases. So that is going to be my first step. If those aren't elevated, then the next thing I'm going to be thinking about is, okay, I've got a dysbiosis pattern here that's associated with inflammation, and I'm not the patient's not manifesting inflammation yet. So should I consider modulating the microbiome in such a way that is going to essentially help to reduce inflammation? So I'd be thinking about our probiotic support, prebiotic support, and looking at the rest of the commensal balance aspects in that commensal bacteria chart to really help with microbiome modulation, and maybe some dietary interventions that would help support that. We saw that some of the bacteria that are associated with inflammation are also associated with diets that are high in fat and high in animal products. So that might be something I would be looking into, and just looking at the rest of the report to see what might be some of the sources for inflammation.
You did mention calprotectin. Is there a specific cutoff value that you're looking for that might prompt you to consider a GI referral or further imaging?
That's a good question. So, with calprotectin, I tend to be pretty darn conservative, because in general, most people should not be secreting calprotectin into the stool sample at all. So cutoffs, I tend to think of cutoffs as if calprotectin is greater than 120, certainly this indicates a need for GI referral. This is something that is looking like some type of potential relapse or indicator of inflammatory bowel disease. If it's in between 50 and 120, I'm still very, very suspicious about what that means clinically and whether this patient is walking the path down an inflammatory bowel disease. And I still might even consider referral in that particular instance, because like I said, I really don't want to see levels of calprotectin showing up at all in the GI tract.
I just want to inform everybody that's on the webinar, I was actually able to upload the PDF version of the research article that spoke regarding the development of the IAD score. So please go into handouts and go ahead and download that. The other question we received was, how do we follow up with a methane dysbiosis score that is elevated?
You know, with an elevated methane score, I would probably follow up with a SIBO breath test to confirm that there's elevation in methane in the GI tract. And then correlating that to clinical symptoms, you know, the American College of Gastroenterology paper didn't speak to whether or how to treat that specifically, whether that should be treated in all situations. But if a patient has been struggling with long-standing constipation, slow transit time, and they have elevated levels of methane and even elevated methane dysbiosis score, then I would think that antimicrobials would make a lot of sense, especially if they're mounting or showing some other evidence like potentially pathogenic bacterial infection. As we talked about, higher levels of methane suppress fecal secretory IgA and eosinophil protein X, those immune markers. So if I'm seeing a high production of methane, a low immune response, and then potential pathogens on board, I think that's a really great avenue to investigate whether this patient can benefit from some antimicrobial therapy.
In regards to fecal secretory IgA, when we have an elevation, can you list what some considerations in terms of why is it elevated in the first place, and what might we consider in terms of follow-up testing options?
Yeah, so, you know, like I said, I tend to think of fecal secretory IgA as sort of like a canary in the coal mine marker, because it's very nonspecific. Anything that is perturbing the mucosa of the GI tract can result in an elevation of fecal secretory IgA. So that can be something as simple as a dysbiosis or a potential pathogen. That can be permeability concerns. That can be erosion of the mucus layer, because IgA is our first line of defense. So actually, I tend to think of it, it's more so our second line of defense, and our first line of defense is the mucosa, the mucus layer. So as that mucus layer is eroded, and then we start to mount more and more fecal secretory IgA, and that can be in response to, like I said, inflammation, potentially pathogenic bacteria, our diet, permeability concerns. All of those can play a role.
There are so many other great questions I would love to ask, but I do want to be respectful of everybody's time. So we're going to end our Q&A period there. And for additional educational materials, we'd like to encourage you to visit our website, www.gdx.net, and/or you can contact client services. We also offer complimentary appointments with our medical education specialists to answer questions related to our testing, including how do I choose what is the right test for my patient, as well as reviewing patient test results. We'd like to encourage you to register for our upcoming webinars on www.gdx.net. As a reminder, we also offer many non-invasive collection packs that can be shipped directly to your patients for specimen collection at home, and the requisition can be completed online. For further instructions, please check out your MyGDX account. And lastly, if you have not already, please check out the Genova Diagnostics podcast, The Lab Report. It focuses on functional and integrative medicine, specialty laboratory diagnostics, and natural therapeutics. And one of the hosts is our very own Dr. Michael Chapman, as well as Dr. Patty Beavers, and the assorted guests that participate in this as well. Again, Dr. Chapman, I'd like to thank you for spending a little bit of time with us today. I hope everybody is as excited about these new GIFX report upgrades, basically using data and science to really advance the field of GI medicine. I hope that you all have a wonderful day. Stay safe and stay healthy. Thank you.
Thanks, everyone.